So we are moving away from triangle congruence, and we're going to talk about similarities. So once again, triangle congruence, two shapes are congruent if they had all the same sides and all the same angles. Similarity is something similar to congruence, but we're going to talk about what's different about similarity than congruence, and how can we show whether two shapes are similar or not, and what does that mean and how we can use that information. But before we get started, we're going to do this warm-up. So we want to dilate this triangle by a scale factor of 2. So thinking back to our transformations, which was like the first thing we learned this year, we had a couple types of transformations. We had translation, reflection, rotation, and dilation. So we want to dilate this triangle by a scale factor of 2. We have our center at the origin, and we have our scale factor of 2. What do we do in order to dilate? How do we go about that again?
Yeah, how many meters from the origin and then multiply.
Alright, so I look for my coordinates of each of my points. So if I look at this first point, it's 1, 1. Ooh, I'm on the second. So I take 1, 1. I then need to multiply that by my scale factor, whatever my scale factor is in the problem. In this case, it's 2. And that gives me my new coordinate of 2, 2, because I multiply these values by 2. So I can plot this point, 2, 2, from my center. And that is my new point of that triangle. So I need to do this with each of my points, and that will give me my new dilated triangle. So my next point is 1, 3. If I multiply 1, 3 by 2, that gives me 2, 6. So I can go over 2, up 6. Have that point. And then our last point is 3, 1. Same thing, multiply by 2. And that gives us 6, 2. 6, 2. And so we have this new, larger triangle.
That is huge.
All right. Picture kind of here a little bit. My triangle's going to be off, but we'll pretend it's there. What do you notice about our larger triangle compared to our smaller triangle? Oh, I'm going to grab this whole thing. 1, 2. There. Okay. I'm going to give up on that. All right. What do you notice about our larger triangle compared to our smaller triangle?
It's still in the
Specifically the side lengths.
3 times.
What? So each of our side lengths are 2. My goodness. Sorry, guys. Each of our side lengths are 2 times longer than our original. So, for example, we have one side length original. I can spell words. We had one side length that was 2. It went to 4. We had one side length that was. Yeah, I think they're all. Well, this is like 2.5 or 2.24 or something like that. But we doubled each of those sides because of by that scale factor. So this is going to relate into similar shapes. We're going to talk about what makes two shapes similar, and it kind of deals with a little bit of a scale factor and things like that. So on your next thing on your paper, you have 2 pictures: a picture of similar triangles and a picture of not similar triangles. Try to determine based off these 2 pictures, what is it required for 2 triangles to be similar to each other? So what are some things that 2 triangles need to be similar to each other? So take a moment, analyze those pictures, and see what you can determine. Okay, so looking at these 2 triangles, what were some things we picked up?
Same angle.
All right, they have the same angles. So 2 shapes that are similar have to have same angles. Good. What else did you notice?
The sides are like added, like 5 plus 5 is like 10. Or
Okay, good. I'll go with the multiples of each other.
It's dilated by 2.
Yeah, it's like a scale factor of 2. Good.
Yeah.
Multiples.
at least we should have one day where we go speak for like first person.
Thank you.
There we go. We'll get real rude.
All right, so the corresponding sides have are multiples of each other. So 3 to 6, 4 to 8, 5 to 10, those are all multiples of 2 of each other, or
And it has the same angle.
and we have same angles. Good, good. And so we look, our not similar did not have these things. Our not similar triangles, they had different angles. Our side lengths, so 2 and 4 are a multiple of each other, but that's not the same as 2 to 3 or 2.83 to 5. All of our same side triangles, all those corresponding sides, were the same multiple of each other. It was always twice the size. We got that scale factor that Colton mentioned. So we're going to throw in another word rather than just using scale factor. We're going to throw in another word called proportional. So rather than saying they're multiples of each other, the side lengths can be proportional to each other. Proportional to proportional. All right. So in order to talk about proportions and proportional sides, we need to do a quick refresher of our proportions that we talked about, or that you probably learned in like 6th grade or whenever you learned about proportions before me. So proportions are equivalent fractions. So when you have two equivalent fractions, you can create a proportion. So what are some equivalent fractions to what we have up here? 3 over 6, okay.
4/8.
4/8, good. So those are all equivalent fractions of 1/2 and 2/4. If we were to simplify those fractions, we'd all get the same answer. So this is like similarity because all of those side lengths, the corresponding side lengths, create equivalent fractions. They create proportional fractions. So corresponding sides create equivalent and so we can create these fractions by taking one of the side lengths and its corresponding side length on the other shape and like putting one in the numerator, one in the denominator. We'll talk specifically about which one goes in the numerator, which one goes in the denominator when we get there. I didn't spell equivalent right. It's an A. All right. So we also need to remember how to solve proportions. With similar shapes, we're often solving for missing side lengths. You know the shapes are similar. Use that knowledge that when you solve for missing side lengths, so we'll often have to set up proportions and solve them. So looking at this proportion down here, how can we go about solving this? What can we do?
Could you multiply 2 times 9, 18, divided by 6?
What were you going to say, Alex?
I was just gonna say, like, multiply like your fraction by like 3 because you know like 9 is a multiple of 3.
I always do for
So yeah, 2 over 3 multiplied by 3 over. Wait, no.
Amanda always went for every 2, there would be 3, like kind of ratio wise, and then how many times can 3 go into 9, and then that's what you times.
So there's lots of different strategies for this. And so whatever strategy works best for you is the way to go. You can use a little algebra and think, okay, I need to solve for x by getting x by myself, so I need to get rid of that 9. It's currently being divided, so the inverse operation of division is multiplication. So you can multiply by 9, and then 9 times 2 is 18, divided by 3 is 6. Right at 6. That's one way to go about it. You might be able to visualize it, like think like how many 2s or how many times does 3 go into 9, and how many, so I can multiply that by 2. Think, okay, 3 goes to 9 3 times, multiply that by 2, 56. That's another way to go about it. Another way that you probably learned 5th, 6th grade, I don't know exactly what, is cross multiplying.
Yes. My.
How do you want it?
Yeah, that was a great one.
Okay. Cross multiplying. So in order to cross multiply, we take our numerator and our denominator from opposite fractions, multiply them together, so 2 times 9 gives you 18. Do the same with the other fractions, so 3 times x equals 3x. And then we can divide to solve for x. And we get x equals 6. That's another way to solve. So whatever strategy really works for you, that's fine. I think cross multiplication is probably the simplest because it'll work whether x is in the numerator, denominator, wherever it is. So it's probably the easiest in my opinion, but it's not the only method. It just works for me.
Rather than we called it catalog. Why? That's just right. Dude, she taught the ways like look.
So she didn't call it cross multiplication, she called it cattywampus.
That was like the
Okay.
So then it just is.
Yeah, it's just,
Whatever.
So if you want to call it cattywampus, go for it.
yay!
All right. So that was our quick refresher on proportions. Now we want to talk about how we can actually use similar triangles to help us solve, or how we can sort of identify these similar triangles. So just like we had a special symbol for congruence, so that was our congruence symbol. That squiggle,
What's about?
that means similar. So if you see that word, that little squiggle, that means two shapes are similar to each other. Yeah, so we are told that triangle ABC is similar to triangle DEF. We want to figure out what is the scale factor that multiplies from our first triangle to our second triangle. So as we do this, always know that that second triangle, that's always going to be, yeah. Yeah, so that's sort of like the answer, or like the product of your multiplication for your scale factor. So what number?
3.
Okay, how do you come up with 3?
Because you could 5 goes 52 times, or lose it 12 times.
So in order for shapes to be proportional to each other, in order for shapes to be similar, that's at the proportional side. So I can look at what are my corresponding sides, and I can create those proportional fractions. So 15 DF relates to AC. Those are my corresponding sides. So 15 over 5.
Oh my gosh, or A, B, C, D, E, F. That's 3.
So
A, B, C.
that's the same as 12 over 4, which is the same as 21 over 7. They're all proportional. They all give you that same scale factor. Once again, though, I use my second triangle as my numerator, and my first triangle is always going to be my denominator with these similar triangles. Otherwise, if we flipped it around, we would have 1/3, which a scale factor of 1/3 wouldn't give you a larger triangle, it would give you a smaller triangle. So just make sure your numerator is going to be your second triangle or your denominator. So let's use the same idea. See if we can find the scale factor from ABCD to A prime, B prime, C prime, D prime with those trapezoids.
No, this is what we just said.
How can we find that scale factor?
Instead of having your first one as your denominator, have that as the numerator.
Have this as your numerator?
Yeah.
Wouldn't that mean that it's bigger?
So if we have a larger number in our numerator than our denominator, it's going to
Didn't you
increase.
say that was a denominator, so you would want it to be the numerator, so it would be small?
So you always want your second shape to be in the numerator. So if A prime, B prime, C prime, D prime is the numerator, that means 3 for AB is going to be above 5 for my original.
Oh,
And so 3/5 will be my scale
then
factor.
I meant it would be the opposite way.
Okay,
That's what I was trying to get.
gotcha, sorry. So 3/5, that will also be equivalent to 1.8 over 3, which is equivalent to 3 over 5, which is equivalent to 6.6 over 11. All of those equivalent fractions are the same. For the scale factor, we like to use that most simplified version though, so 3/5 is our most simplified fraction. So that would be your scale factor that I would write down. Just as 3 was our most simplified fraction, 3 over 1 in a sense is our scale factor. But anytime you need to find those scale factors, just take your second value, put it above your first value of the corresponding side, and that will give you your scale factor. Are we okay with this?
Wait, that was your scale factor?
Mm-hmm. Yeah. 3/5.
Oh.
They all equal the same number, so if you were to divide, you would all get the same decimal place, but we want that simplified fraction as the scale factor. So 3/5 is our simplified fraction of that number. All right, so now we're actually going to use similar triangles or similar shapes to help us actually solve for missing things. So I'm told triangle ABC is similar to triangle TJF. So I want to figure out what is the value for X and what is the value for Y. So we'll have to think, what are some things that happen when we have similar shapes that help us solve for these missing pieces of information?
Angle.
So we know all the angles are going to be the same,
Probably.
and we because remember that picture we saw with all those two similar triangles, they have the same angles. So we know that will help us solve for our angles. And then we know the sides are always going to be proportional. So we'll have to use those two pieces of information to help us find these missing pieces of our triangle. So which one do you want to solve for first, x or y?
X.
X, okay. So x is a side length, specifically side length BC. Which side length does that correlate to on our other triangle?
JL.
JL. So JL is 30. So JL is our second triangle, or comes from our second triangle. So 30 is going to be the numerator over x. So that's kind of our scale factor. We'll have to figure out an equivalent fraction, a proportional other, or another set of proportional sides to this one, to be able to solve for x though. Because right now, 30 over x, we can't solve that. We have to create an equation. So what is this equivalent to? What's another set of equivalent sides we could use?
ACL.
18 over 15. So 18 is from our JT, which matches with BA. So 18 over 15. From here, we have a proportion set up, so we can just solve for the missing pieces using whatever method you like. I'm just going to cross multiply. So 30 times 15, that should be 450. That equals 18x. From here, we can just divide by 18, which should give us x equaling 25, I think.
How did you do the 30 times 15?
I remember from previous classes.
You
You can also think 30 times, or 3 is 30 times 15. 15 times 3 is 45. Multiply by 10 to make it actually a 30 instead of a 3. And that's 450. So 3 times 15 is 45 times 10 is 450.
So X is 25, that's our.
Yes. And I mean, you'll have a calculator, so you don't have to in your head. Just mine. Alright, so X is 25. So we found our side lengths. So anytime you're solving for those side lengths, you need to find one pair of corresponding sides that you know both values of to set up that equal equation, and then be able to set up your other fraction to be able to solve for x, and set them equal to each other. But we still need to solve for y. We know similar triangles and similar shapes have equal angles. So we have to figure out what angle is going to match y on my first triangle.
Why does the first one have the dashes? Congratulations.
Oh, I think this is just saying 53.13 is supposed to be this one here. Okay, that's what it's supposed to say.
C and M.
So C and L are corresponding angles. But the thing is, we don't know what angle C is right now. So we can't use that to help us find L, can we? Or is there a way we can solve for C?
Wait.
How can we solve for C?
Oh! Oh my gosh! I actually did that.
So all of those angles are going to add to equal 180 degrees. So we can take 180 degrees minus our other two angles, and that leaves us with what we have left for C. So 180 minus 53.13 minus 90 leaves us with 36.87, I think. The answer, I believe. So that gives us 36.87 for here. But because we know they're similar, we know they're the same, which gives us 36.87 for y. So good. So with similar shapes, if we know shapes are similar, we can solve for their missing angles, or we can solve for their missing sides because we know there's two different properties of similar shapes. So on this next one, I want you to take a moment and I want you to try to solve for those missing properties. So see if you can solve for x, see if you can solve for that missing side length on this one. So what did we find for x? 6. How did you go about that? What do you do?
You have to see that B and C are the same, so 3.
So x and 3 relate?
I think 3 over X.
So B prime is C prime, and because as a prime we know it's going to be the second value, it's going to be the second shape. So technically if you're going for a scale factor, this would be in the numerator. You'll get the same answer by flipping it, But if you're looking for the scale factor, we will want to put this one on top. So it's okay, you did it the other way. You still got the same answer, you still got the right answer. But if you're actually looking for the scale factor, which we aren't on this problem, so it doesn't matter, you just put that one on top. And then for number 2, I assume. And then from there we can cross multiply, which gives us 6x equals 12 divided by, sorry, 2x equals 12 divided by 2. We get x equals 6. Yeah. I don't know what I was thinking about. All right, so we have 2 more problems. All right. So our first one, we have triangle ABD is congruent to triangle GFD. And we want to find that length of CD or DC, I'm sorry. How would you go about this? So I'm told that triangle AC or ABD, all over the place, ABD, this relates to triangle GFD. So I need to see what are my corresponding sides. So DC is my sort of perpendicular angle bisector that I have going on, or my altitude, as we'll learn later. That's going to relate to my altitude of my other triangle. So
Well, then you can also look at.
are you okay? Alright. So we'll have to figure out some variable for this. So I'm just going to call it x in this case. So x, that's going to relate to 20. GFD is my second shape, my second triangle, so I'm going to put 20 in my numerator over x. I need to find what is the corresponding side that relates to this. So what would you use as your other values? 8 over 6, okay. So we see 8 corresponds to 6 on our triangles. From here we can cross multiply. 6 times 20 is 120. X times 8 is 8x. Divide by 8. Divide by 8, we get x equaling 15. Are we okay with this one? Solving those proportions? So that's a big thing, just being able to set up those proportions, be able to solve for those missing sides. That's just a big practice with similar triangles. We have one final thing we're going to talk about. We want to show that these two triangles are similar, or we want to discover, are they similar and why? So if we remember, similar shapes have 2 things. They have proportional side lengths, and they also have the same angles. So we have to show both of those, same side lengths and same angles, in order to show that they're similar or not. Which one do you want to start with, side lengths or angles?
Angles.
Angles? Okay. So like what we did earlier, how can we find this missing angle? 180 minus 90 minus 30 gives us 60. So 60 is our missing angle. Same thing for our other one, 180 minus 90 minus 60. That gives us 30. So they're both 30, 60, 90, so they have the same angle. So that's one check. But they also need to have those proportional sides as well. So we have one part correct.
Do we have to do like all of the math? But if it's like a simple, like you see it and it's like you know, you still have to write it all out.
Yes, if you can see it, you can write it out, or you can just write it. But if it's wrong and you don't have that math, I can give you partial credit. So if you want that partial credit, in case you get it wrong, write out all your work. If not, I can't do anything, and you just got the whole problem wrong. So just be cautious with that. So that's why I always recommend doing partial credit. So with proportional sides, we just have to show that they're equivalent fractions. So 230, or 2.30, that's corresponding with 1.15 on my triangles, because it's opposite of my 30 degrees. I need to show that this is corresponding to 4 and 2. So if I did 2.30 divided by 1.15 to create this, figure out what this fraction equals, my simplified fraction, it gives me 2. 4 divided by 2, that's also 2. And so because they're the same, they are proportional. So because it has proportional sides and proportional angles, we can say our triangles are similar, but only after proving both of them. We have to show both things are true.